In this module, we will discuss the orbits of satellites in medium to high Earth orbit, including geostationary satellites, which are very important for global meteorological observations, and a focus of the second lecture series that will follow. The orbit of a satellite is important primarily because it controls the area that we can see from the satellite, and also puts a physical constraint on the spatial resolution that we can achieve. It also impacts the projection of a satellite image. In the Python code for the first lab, you can actually see where the map projection for the data must be specified. Particular attributes of an orbit determine how much area a single satellite can cover, how high a latitude it can take observations, or what the return time is for a satellite at a given point on Earth. An orbit is defined by a few characteristics, the first of which is height. We will discuss orbits in three categories of heights. Geosynchronous orbit, which is about 35,786 kilometers above the surface, and is where satellite platforms like GOES, Himawari, Meteosat, INSAT, or Fingyun operate. Mid-Earth orbit is essentially anything below geosynchronous orbit and above about 2,000 kilometers. Semi-synchronous orbits are examples of mid-Earth orbits. Low Earth orbits are less than 2,000 kilometers above the surface, and most that we will talk about in this class are under 1,000 kilometers in altitude. The majority of satellite systems, in fact, that we will discuss in this class are in low Earth orbit. A geosynchronous orbit is completed once daily. Satellites in low Earth orbit or at lower altitude move more than twice as fast and complete a full orbit much more frequently. Eccentricity is the next important parameter used to describe an orbit. It describes the shape of the orbit and is denoted here by epsilon. Eccentricity of 0 describes a perfectly circular orbit, while higher eccentricities describe elliptical orbits with foci that are increasingly far apart, and one of which is always Earth. The orbits for most of the platforms we will discuss in this class have low eccentricity, like close to 0, meaning that they are nearly circular. You can see how the orbit with the high eccentricity, closer to 1, looks much like an ellipse. A couple of additional terms come up when discussing elliptical orbits: apogee and perigee. Apogee refers to the point in an orbit that is furthest from the major focus, which is Earth for remote sensing satellites. So this in the example of the elliptical orbit. Perigee is the point of closest approach to Earth. Other orbits have these parameters too. For example, Earth's orbit around the Sun is not perfectly circular. It reaches apogee, or aphelion, in July and perigee, or perihelion, in January. An orbit is also defined by its inclination. The inclination describes the angle off the equator made by the subsatellite path of an orbit. Imagine if you drew a line in the ground pointing straight down from a satellite and drug it along the ground as the satellite moved. That would be the subsatellite point. We call the viewing geometry of the satellite pointing straight down from the satellite nadir, or Nadir. An outline of one hypothetical satellite track is shown by the red line in this figure. The angle denoted by the black arc is the orbital inclination. In this example, it looks to be about 45 degrees off the equator. Geostationary orbits have inclination, as we will soon see, of 0 degrees. And a hypothetical orbit directly over the poles would have an inclination of 90 degrees. A special type of low Earth orbit, Sun-synchronous orbit, has an inclination of around 98 degrees, which is denoted by the blue line. That means that the highest latitude over which it will pass is 82 degrees, although onboard instruments may be able to sample off nadir at higher latitudes. Orbits with inclination larger than 90 degrees are in retrograde orbit, which means that they appear to move from east to west on successive orbits. Prograde low Earth orbits are those with inclination less than 90 degrees. As stated before, the orbits for most satellites we will discuss in this class are close to circular. However, there are several factors that make the orbit slightly elliptical or require occasional correction to maintain the desired orbit. The most obvious is that the distribution of mass on Earth is not spherical. The Earth's geoid has numerous fluctuations in space, which also becomes important to consider when collecting measurements with an altimeter. Other bodies, particularly the Sun and Moon, also exert gravitational force on satellites. Especially for satellites in low Earth orbit, drag and lift are dependent upon properties of the satellite platform itself, and must be accounted for because they cause the orbital velocity to be a little different than that predicted by Newtonian mechanics. At least Newtonian mechanics when we neglect friction. Other processes associated with solar radiation and Earth's electromagnetic field can cause higher order minor alterations to orbit that can vary with time. Occasionally, corrections must be made to an orbit by using fuel to thrust the satellite platform in a direction that increases or decreases its forward velocity in order to maintain a stable desired orbit for observations that are consistent and high quality for many years. Next, we'll look at geosynchronous orbits, and in particular the special case of geostationary orbits, in more detail. A geosynchronous orbit is any orbit at the height of about 35,786 kilometers above mean sea level. It can have any inclination, and a variety of combinations of inclinations and eccentricities can be used to create various orbital patterns. The main characteristic of geosynchronous orbits is that they return to the same zenith, or overhead, point every 24 hours. So one example of a geosynchronous orbit could be this red circle here. A geostationary orbit is a special case of geosynchronous orbit as denoted by the simple Euler diagram down here. Its inclination is 0, as indicated by the black line up here, which is exactly perpendicular with the axis of rotation of Earth. The fact that the inclination is 0 means that it is neither in prograde or retrograde. This means that a stationary orbiter remains over the same subsatellite point all the time. A geostationary satellite is therefore often defined by the longitude of its nadir viewing angle. In other words, it views the same scene continuously. This is extremely useful for making observations of Earth with high temporal resolution. The entire second lecture series is devoted to interpreting measurements from advanced imagers aboard the United States GOES and Japanese Himawari weather satellites. The velocity and height of a geostationary orbit can be determined analytically easily by using Newton's laws of motion. Remember Newton's second law, which states that the force needed to accelerate an object is proportional to its mass. Perhaps you recall from a university course in kinematics that centripetal acceleration is velocity squared of an object divided by its orbital radius, the latter of which is the difference from the center of rotation, in this case Earth's center of gravity. Note the expression for gravitational force between two bodies, which is proportional to the product of the masses of the two objects, and as stated earlier, inversely proportional to the orbital radius squared. If we equate the two to each other, then the mass of the satellite becomes inconsequential to its orbital velocity. Although a large aerodynamically so-called sticky satellite may have more drag and make its orbital velocity a little slower than that predicted by Newtonian mechanics laid out here that neglect friction. We know that the orbital period is just the distance of the orbit, which is approximated here as the circumference of a circle, divided by orbital velocity. Then do some algebra to solve for the orbital period, or given the period, solve for the radius. Try this and see if you can mathematically show what the height of a geostationary orbit is. An example of the view from a geostationary satellite is shown in this image, taken from GOES 16. As you can see, the entire disk of Earth is visible. If you were able to zoom in and look closely, you can see that the spatial resolution is higher at nadir than it is at the edges of the disk. Nadir would be right down here, and the edges, of course, out here at the edge of the circle. An image like this can be collected currently every 15 minutes, with imagery over smaller sectors, such as over the United States, collected more frequently. As mentioned before, one of the benefits of geostationary orbit is its large spatial coverage that is continuous. However, the spatial resolution is not very high. The highest resolution of any GOES data nadir is 500 meters by 500 meters. For comparison, we will see later in the course some examples of low Earth orbit satellites that can achieve resolution on the order of a few centimeters. The distance also makes active sensing impractical. Furthermore, as seen in the previous image, polar regions are not well observed, and the high latitudes that are observed are done so at coarse spatial resolution. Finally, geostationary satellites experience temporary outage during eclipses, although this is not so frequent. We'll finish this module by briefly discussing a couple of medium Earth orbits, the Semi-Synchronous Orbit, and then we'll discuss the Moneo Orbit. A semi-synchronous orbit is situated at about 20,200 kilometers above mean sea level. The image shown here is not to scale. The Earth is way too large compared to the orbits, but it just illustrates that the semi-synchronous orbit in green is always inside a geosynchronous orbit with the same inclination, which is shown in red. Satellites in semi-synchronous orbit move more quickly than those in geostationary orbit and complete one revolution every 12 hours. The primary use for semi-synchronous orbit discussed in this class is data derived from GPS satellite constellations. GPS operates at an inclination of about 55 degrees, and GPS radio occultation is used to derive profiles of temperature and humidity in the atmosphere. Finally, the Moneo orbit is seldom used for Earth science purposes, but is highly useful for viewing or transmitting to or from high latitudes. The orbit, as you can see in the bottom right here, is highly eccentric, and it has an inclination of about 63.4 degrees. The rotational period, or the orbital period rather, is about 12 hours, and it has an apogee of nearly 40,000 kilometers, which is comparable to the distance that geostationary orbiters sit at. The orbital velocity varies with distance from Earth, increasing as the satellite passes closest to Earth at the perigee down here. This means that the subsatellite point of a platform in Moneo orbit is usually over the high latitudes. This is useful for purposes such as communications at high latitudes, where geostationary platforms are not very effective. An example of the subsatellite track of a Moneo orbit is shown at bottom left. And it would do something, if I'm using my mouse cursor, it would go really fast down here, and then kind of slow in the northern hemisphere, and then really fast, and then kind of slow up here, and then really fast again. So it spends most of its time over the northern hemisphere. And you can also see that in this plot to the bottom right. Because the orbital period is 12 hours, successive orbits view opposite sides of the globe. So in one orbit you see Canada, the other orbit you see Russia. For Earth science purposes, a constellation of satellites in such an orbit could be useful for viewing weather or sea ice, for example, at high latitudes. In the next module, we'll discuss low Earth orbits in more detail.